Hello everyone, I'm Akhilesh Kumar Srivastava from ABES Engineering College, Ghaziabad. In the last lecture, we have discussed about the programming of the breadth-first search. In today's lecture, we will extend that concept to find out the shortest distance between the source and the other vertices using the BFS. So let's say this is the graph given to us, and we have been asked to find the shortest distance from vertex number 0 to the other vertices. To find this, we will use the concept of the BFS only, but with a very slight change. Let's take a status vector here that will be representing the distance from the source to the other vertices. Let's say the vertex is 0, then 1, then 2, then 3, and then 4. We are initializing each of the distance here as -1. Instead of writing 0 that we did in the BFS, we are writing it -1. The meaning of the -1 here is unapproachable vertices. It means if a vertex is not approachable from a vertex, source vertex, we'll say that that is unapproachable. So here we have assumed that all the vertices are unapproachable initially. Now we'll take a Q as we did it earlier in the BFS. So this is the Q. And we are inserting the source vertex. Let's assume that the one number vertex is the source here. So vertex number 1 has been inserted in the queue. Now, we are going to set the distance of 0 as 0. This is obvious. It means if we have the source vertex, then the distance of source from source will be 0. Then we are going to delete this 0. We must have designed first the adjacency list. Let's write that here. From 0, the connections are 1, 4. From 1, the connection is 0, 2, 3, and 4. From 2, the connections are 1, 3. From 3, the connections are 1, 2, and 4. And from 4, the connection are 0, 1, and 3. So we're going to see the connection from 0. So the 0, the connections are 1 and 4. So this 1 and 4 have not been explored earlier. -1 is indicating that they have not been explored earlier. If this value was 0 or something positive, we could have said that these vertices have already been visited. So since these have not been visited earlier, so we're going to push them on the queue, and we will set their distance in the status. So their distances will be set as 1 more than 0. Since 1 and 4 have been explored from 0, their distances will be set as 1 more than 0. So the distance of 1 is set as 1, and the distance of 2 is also set as 1. 0 plus 1, 1. Then we're going to delete this 1. The connection from 1 are 0. The status of 0 is 0. It means that vertex has already got visited. 2, this vertex has not got visited earlier. Sorry, we have made a very small mistake. Instead of writing 1, the distance of 2, we should write it the distance of 4. Okay, so 2 has not got visited earlier. This is its status is marked as -1. So let's mark its status as 1 more than the distance of 1. It means the distance of 2 will be 2. We should push this on the queue as well. Now the next connection is 3. 3 has also not got visited earlier. So the distance of 3 should be set as 1 more than the distance of 1, because 3 is getting explored from 1. So the distance of 3 is set as 2. And this vertex will be inserted in the queue. Then the 4, which has already got visited, its status is 1. So all the connection from 1 is over. Let's delete this 4 and see the connection from 4. So connection from 4 is 0, already visited, 1 already visited, 3 already visited. So let's delete this 2, and the connections are 1 and 3. So 1 and 3 both have already got visited. Then we are deleting this 3. We can see that the connections are 1, 2, and 4, which have already got visited. So in case we write this status vertex once again, fresh here. So the values are 0, 1, 2, 2, and 1. Now you can see that if you go from 0 to 1, only one edge is involved. And the cost of this edge is considered as 1. So the shortest distance from 0 to 1 is 1. Similarly, if you have to go from 0 to 2, then the two edges are involved. One is this one and another one is this one. So the distance of 2 is 2. Similarly, if you have to go to 3, you can follow either of the path, either from 0 to 4 and then 4 to 3, or from 0 to 1 and 1 to 3. So in both the cases, the distance is 2 because two edges are involved in this path. The distance of 4 is 1 because there is a direct edge from 0 to 4. So hence the distance of 4 from 0 number vertex is 1. So this way we can find out the shortest path between the defined source and the other vertices in the graph using the BFS method. Let's try to write the algorithm for the same. Since we already have an idea about how to write the BFS, this is going to be very simple for us to write. So BFS, shortest distance. So this is the name of the algorithm that we're going to write. The parameters here will be the adjacency list, which is a 2D array for us, and a source will be defined here, and the number of vertices, which is V. So what we are going to do, we will have to take a Q. Let's say the Q is Q. And then we need to take a status vector. And all the values in this status vector has to be defined as -1. I'm writing it as -1. You will have to write either -1, -1, -1, or you will have to apply a loop here. So I'm just doing a shortcut by writing -1 here, and you should consider that this is actually treated as the initialization of all the vertex status as -1. Although this is not correct, just please assume this. Now after this, let's take the source vertex and try to push this source vertex on the Q. In the algorithm, we write NQ. So in the Q, let's try to push this vertex number S, and let's define the status of the source vertex as 0. Now we'll perform, or we'll keep doing the operation while Q is not empty. So while not is empty Q, we'll keep doing our work. We are going to delete a vertex from the Q. For this, we need to call the DQ function, which will delete a vertex. Let's say that vertex is X. And then we'll look for all the connection from this X. So for each J that is element of adjacent to X, of adjacency list, in the adjacency list X, whatever values are there, we'll say that that is J. We'll have to see the status of this J. So if the status of this J is unmarked, it means if the status of this J is -1, then we should visit this vertex. For doing so, we will mark the status of J as the status of vertex number X +1, because this vertex is going to be explored from this X, hence the status of J should be 1 more than this status of X. And similarly, we should NQ the vertex number J in the Q. Fine. So whatever is the data value in this status vector, those are the distances. So finally, what you can do, you can return the status vector, which will be containing the distance of all the vertices from the given source. But let's try to implement this using a very small code. For implementation, we will take the previous code only. I think you'll remember that how to write the code for the BFS. We're taking that as a base. We are taking this Q here, and then we are taking a vector. In the earlier BFS code, we have started with the status 0. Here we are starting with the status -1. Then we are going to push this 0 number vertex. We are considering that 0 is the source in the Q, and then the status of vertex number 0 will be set as 0. because this is the source vertex. So by the time the queue is not empty, we are taking one vertex from the queue front, then we are deleting the queue vertex, then we are looking at the connection from the X number vertex, whatever those connections are, we are taking them one by one in, let's say, variable y. So if the status of y vector is not visited, we'll show that by -1. Then the status of y will be set as the status of status of x plus 1, because this is getting explored from vertex number x. And then we're pushing this vertex on the y. Fine. So no need to print x here. We used to do this in the BFS. When the operations will finish, we will have to print the data values of the status vector. So for integer I is equals to 0, I less than v, and I plus plus, we're simply going to print the values of the status vector. Just apply a space here that will show actually the distances from the vertex number I. Let's run this code and see if this code works fine. Now this was the graph that we took. We'll take the same graph again here, and first we should draw the adjacency list. So making the entry of the graph, the number of vertices here are 5, the number of edges here are 7. The endpoints of the edge 1, getting it in the sequence number. So edge number 1 is 0 and 1, edge number 2 is 0 and 4, edge number 3 is 1 and 2, edge number 4 is 1 and 3, edge number 5 is 1 and 4, edge number 6 is 2 and 3, edge number 7 is 3 and 4. So here you can see that first we have represented the graph adjacency list, and then here is the data value which is representing the distance from source to the other vertices. It means the source to source distance is 0, and then the distance from source to vertex number 1 is 1. From source to 2, it is 2 distance, source to 3, it is 2 distance, and source to 4, it is 1 distance. So this is a very useful concept of finding out the shortest distance from source to the other vertices using the BFS method. This can be utilized for solving many problems at the HackerRank and the Lead Code platforms. This will be very helpful for you to solve the problems which are asked usually in the competitive examinations, the placement recruitment processes, and so on. So thank you so much, students, for watching this video. We'll meet again in the next video with the programming of the DFS and the many concepts that can be extended with the help of the DFS. Thanks again.